Okay, so let's jump right in. You've heard of the celebrity numbers in math, right? Like pi. You can't have a circle without it. But what if I told you there's another number, just as huge, but way more mysterious? It's the number that governs how things grow. Today, we're going to pull back the curtain on the number e.
Yeah, I'm serious. If pi is the boss of circles, then what's the number for growth? Turns out, there totally is one. And it's not some obscure thing. It's everywhere, hiding in plain sight, from your bank account to the laws of physics.
All right, let's put these two heavyweights side by side. You've got pi, right? Roughly 3.14. It's the solid, unchanging rule for every circle. But then you have e, this weird-looking 2.718, and it's all about motion and change. Think of it as the base setting, the factory default for anything that grows smoothly and continuously. Like a snowball rolling downhill, it's not just getting bigger in jumps, it's growing every single moment.
Now, to really wrap our heads around E, we got to talk about exponential growth for just a second. It's a super simple idea, really. It just means the more you have of something, the faster it grows. You know, like a couple of rabbits. They have more rabbits, and then all of those rabbits have more rabbits. It just explodes. That's exponential growth.
Okay, this is where it gets really cool. We're not just going to talk about E, we're going to build it from the ground up. Let's start with a little story. Imagine you've got $1 single, and you find this miracle investment, a guaranteed 100% return in 1 year. Easy peasy, right? You put in $1, you get $2 back. Case closed. Or is it?
This is where the magic happens. What if, instead of waiting the whole year for your payout, the bank gives you half of your interest, so 50%, after just 6 months? Okay, so after 6 months, you've got $1.50. But now, that extra 50 cents starts earning its own interest for the rest of the year. It's like your money had a baby, and now the baby is earning money too. So at the end of the year, you don't have $2, you have $2.25. You literally made more money just by changing the payout schedule.
And that right there is the key. The real world doesn't work in big, clunky steps. Growth isn't something that just happens, bam, at the end of the year. It's happening all the time, smoothly, continuously. I love how our source material puts it. Mr. Green doesn't just show up out of nowhere. He slowly grows out of Mr. Blue. It's a constant process.
So this obviously begs the question, right? If getting paid twice a year is better than once, what about 4 times a year or 12 times a month? What if we get paid every single day, every minute, every single second? Does this just keep going up forever? Are we on the path to infinite money here?
Well, let's look at the data. We start with 1 payout a year, we get $2. We jump to 4 times, quarterly, and we're at $2.44. Okay, monthly, $2.61. Daily, $2.71. You can see it's going up for sure, but the jumps are getting smaller and smaller. Even if we do it 1,000,000 times, look at that. It barely budges. It's not running away to infinity, it's hitting a wall. A very specific, very strange wall.
And that wall, that limit, that is the number e. It's the absolute maximum, the ceiling, the best you can possibly do with 100% growth in one period if you compound it perfectly, smoothly, continuously, every single instant.
So think about it like this. E is kind of like the universe's speed limit for growth. It's the gold standard. It represents perfect, 100% continuous growth over one chunk of time. Any other kind of growth you see in the universe, it's really just a scaled up or scaled down version of E.
Okay, that's the theory, but how do we actually use it? Well, all this incredible complexity gets packed into one beautiful, simple formula. Your final amount is just your starting amount, let's call it C, times e to the power of your growth rate, k, multiplied by the time t. That's it. That one little equation is the master key for any process of continuous growth or decay.
And I mean it when I say it's everywhere. This is the formula banks use for continuously compounded interest. It's how biologists model population growth when there are no predators. It's how physicists know exactly how long radioactive stuff will take to decay. And for the calculus nerds out there, it has this one-of-a-kind property of being its own rate of change, which is just wild. It's the literal definition of growth.
And check this out. This is a really cool idea. Look at that little k up in the exponent. What that's really telling us is that rate and time are interchangeable. They get blended together into one number that represents the total oomph of growth. So, growing at 3% for 10 years has the exact same overall effect as growing at 30% for just 1 year. It's the total growth that matters. Let's make this real. Take a radioactive substance like fermium-253. We know its half-life is 3 days.
So if we start with, say, 1200 milligrams, how much is going to be left after 10 days? We just pop those numbers into our formula, making the rate negative because it's decaying, and boom, the math tells us we'll have about 119 milligrams left. It's not guesswork. It's perfectly predictable thanks to E.
All right, so this formula is great for predicting what happens next, but what if we need to work backwards? Like with carbon dating a fossil? We can measure how much carbon-14 is left, but the question we really want to answer is how old is this thing? The problem is the thing we're solving for, time, is trapped. It's stuck way up there in the exponent. How in the world are we supposed to get it down from there?
Now, sometimes you get lucky. You get a nice, clean problem like 3 to the power of something equals 81. And you go, oh, I know that. 81 is just 3 to the 4th power. If the bases are the same, then the exponents have to be equal. Done. But what happens when you get something messy, like 4 to the power of something equals 25? Ugh. You can't just rewrite 25 as a power of 4. It's not a whole number. So are we just stuck?
So what's the move here? Our variable is a prisoner in that exponent. Think about it. To undo addition, you use subtraction. To undo multiplication, you use division. Every operation has an opposite, an inverse. So what's the inverse of an exponent?
Say hello to our little friend, the logarithm. That's what it is. A logarithm is the special tool invented for this exact job. It flips the question around. Instead of saying 4 to the power of what gives me 25, the logarithm asks, hey, what power do I need to raise 4 to in order to get 25? It's the same question, just asked from a different angle.
Okay, let's break it down. Step 1. Get the exponential part by itself. In this case, it already is, so that's easy. Step 2, you take the log of both sides of the equation. Fair is fair. Now step 3, this is the secret weapon. There's a rule in logarithms, the power rule, that lets you take that entire exponent and just drop it down in front. It's no longer an exponent, it's just a number being multiplied. Our variable has been busted out of jail. After that, it's just simple algebra. Step 4 is just cleaning up and solving for x.
You punch that into your calculator, and what do you get? You get a real answer. X is about negative 0.678, a number that looked totally impossible to find. The logarithm just handed it to us. Pretty amazing.
Okay, so let's boil this all down. What are the big takeaways? First, E is not some random number. It's the universal constant for perfect continuous growth. Second, that formula, the one with e to the kt, is your master key for modeling pretty much any growth or decay in the real world. And finally, whenever you have a variable stuck up in an exponent, don't panic. The logarithm is the tool that will set it free every single time.
The cool thing is, once you know what to look for, you start seeing the fingerprint of E all over the place. It's in the way your money grows, how populations change, even in the rate your coffee cools down. It's this hidden, universal rhythm. So now I'm curious, where are you going to spot E out in the wild?